Today we're going to discuss hydraulic concepts for the fire service. I'd like to thank Kettering Fire Department for providing the basis for this hydraulics PowerPoint. I would also like to thank those whom I bounced ideas off of to make this more well-rounded. And just so you know, we asked the chief. He won't let us build one of these hose lines as part of our drill. So let's get started. Being a driver-operator in the fire service is not just driving around town with lights and sirens. It is also calculating the right PSI to provide the right GPMs needed to overcome the BTUs produced by the fire. This skill and ability is needed on the fire ground to save lives and property. This presentation is designed to provide an overview of basic fire pump design, fluid dynamics, hydraulic calculations for the fire ground, and troubleshooting pressure loss issues. What we will not cover today are drafting, mounted deck gun, or ladder pipe operations. There are 4 levels of competence that all of us at some point or another have been in for any number of skill sets. The first is unconscious incompetence, where the learner isn't aware that a skill or knowledge gap exists. The second is conscious incompetence, where the learner is aware of a new skill or knowledge gap and understands the importance of acquiring the new skill. It's in this stage that learning can begin. The third is conscious competence, where the learner knows how to use the skill or perform the task, but doing so requires practice, conscious thought, and hard work. The fourth is unconscious competence, where the individual has enough experience with the skill that he or she can perform it so easily they do it unconsciously. Level 3 and 4 are where we as professionals should strive to spend most of our time. This requires a lot of continuous effort and training. There are also 4 levels of hydraulic understanding in the fire service. The thumbs up and thumbs down method is meant to be used as an adjustment for an individual nozzle person. For example, a smaller person might not be able to manage the line with its proper GPM flowing due to nozzle reaction and wants it to be adjusted down. The hand method is taught at many fire service academies. Theoretical hydraulic calculations is used mostly for research. The simple math method. Simple math equations that get the operator close enough to theoretical hydraulic calculations. Practicing this calculation will help us achieve the level of unconscious competence that we want for quick water. Hydraulics is the branch of science and technology concerned with the conveyance of liquids through pipes and channels, especially as a source of mechanical force or control. The fire service pump and equipment are the pipes and channels through which water is conveyed under mechanical force. The equipment covered in this class will include the following: centrifugal pump, used in the fire service because it can move large capacities of water under constant pressure; pressure relief valves and electronic governors; intake relief valves; transfer valves; positive displacement primers; manual pump shifts; gauges; and auxiliary coolers. The centrifugal pump is a non-positive displacement pump, which means that it does not pump a definitive amount of water with each revolution. In the following video, it will show the mechanical inner workings of a centrifugal pump.
Centrifugal pumps are the most preferred pumping devices in the hydraulic world. In this video, we will have a conceptual overview of working of centrifugal pumps. At the heart of the system lies the impeller. It has got a series of curved vanes fitted inside shroud plates. The impeller is always immersed in water. When the impeller is made to rotate, it makes the fluid surrounding it also rotate. This imparts centrifugal force to water particles, and the water moves radially out. Since rotational mechanical energy is transferred to the fluid, at discharge sides of impeller, both pressure and kinetic energy of water will rise. At suction side, water is getting displaced, so a negative pressure will be induced at I. Such low pressure helps in sucking fresh water stream into the system again, and this process continues. This is the reason why priming is important for centrifugal pumps. If no water is present initially, the negative pressure developed by rotating air at eye of impeller will be negligibly small to suck fresh stream of water. Impeller is fitted inside a casing, so the water moving out will be collected inside it and will move in the same direction of rotation of impeller to the discharge nozzle. Here you can note one specialty of casing. It has got increasing area along the flow direction. Such increasing area will help in accommodating newly added water stream and will also help in reducing exit flow velocity. Reduction in flow velocity will result in increase in static pressure, which is required to overcome resistance of pumping system. Here you can see more details of vanes inside impeller. They are backward curved vanes with state-of-the-art eye configuration. This vane is extracted from a Kirloskar pump model. If pressure at suction side of impeller goes below vapor pressure of water, a dangerous phenomenon could happen. Water will start to boil, forming vapor bubbles and spoil impeller materials over time. This phenomenon is known as cavitation. More the suction head, lesser should be the pressure at suction side to lift water. This fact puts a limit to maximum suction head a pump can have. Careful pump selection is required to avoid problem of cavitation.
Three factors influence pump discharge pressure: the amount of water being discharged, the speed at which the impeller is turning, the pressure that the water has when entering the pump. The centrifugal pump can be a single or multi-stage. A single-stage pump uses a single impeller to deliver water with pressure capabilities. A multi-stage pump uses two or more impellers and a transfer valve to allow the pump to create pressure or volume. When in pressure mode, the impellers pump in series. When in the volume mode, the impellers pump in parallel. A centrifugal pump cannot pump air, therefore it cannot be self-priming. Water supplies include, but are not limited to, the onboard tank, a dump tank or other static water source, or even yard and county hydrants. Yes, you heard that right. Yard hydrants can be used for first water. We will focus on the use of positive water sources and relay pumping, since we will cover drafting in a future training. We strive to connect to a positive water source in the form of the county's water system. This is a bit easier on the western side of the township. There are mains made of typical ductile iron and 6+ inch pipes. On the eastern side of the township, hydrants are connected using PVC pipe, which may fracture and break much easier. On any particular scene, the first due may go in dry or lay a tail for a long driveway. The second due can feed them until a positive water supply is established. Consider the next video explaining the anatomy of a pump to better supply operations, if the conditions and equipment are right to do so. Either way, you'll have a better understanding of how pumps are designed and work.
Hey, welcome back to the Roll Steady, the pump series. As we continue to work our way down the supply chain from the hydrants all the way to the tip of the nozzle, before we start talking about what we pump to certain lines or debating smooth fog tip nozzles, really we need to have some basic understandings of the function or the anatomy of the pumps that we're utilizing. We started at the hydrant and then we talked about supply lines and 5 and 3 inch and what we can expect to get from those in terms of volume. Today we're going to talk about that volume as it enters our engine in through these inlets or these intakes. What I want to do is I want to show you a little bit of the anatomy of our pumps, and then I want to give you a demonstration in real time on engine 29 demonstrating this stuff. All right, a quick disclaimer here though. My goal in this is to help you understand this in a way that makes sense, to help you understand the why behind this, not necessarily the what behind this. So in Dallas, our engines utilize a 2-stage centrifugal pump, okay? And feeding that pump are multiple inlets or intakes, okay? We've got our 5-inch intakes. You've got a 5-inch on one side, you got a 5-inch on the other side. We've got multiple 3-inch or pony sections. And then another one that people tend to forget about is the tank to pump. All right, now what's fundamental and key to understand is all of these intakes converge pre-pump into the intake manifold right here. So we're using this term manifold, and don't let that term throw you off, okay? All that means is you've got a series of piping that comes together into a collection point. It allows gases or liquids to enter or exit. That's all a manifold does or is. All right, so we've got this very simplified diagram here. And again, the goal is to help you understand why things are happening the way they're happening when we start pulling and pushing levers. So we've got our pump on one side over here, and then we've got 3 intakes. We've got intake 1, intake 2, intake 3. Okay? And as we open intake 3, we hook a supply line up and we have water coming through. Now water's hitting the pump, okay? Water is also able, because it has this collection point pre-pump, okay? Water is able to flow back down these pipes as well. So what's gonna happen when we open up intake 1? Water is going to exit at the same pressure that it's coming in intake 3. This is the basic function of intake to intake and why this works, how water passes through without hitting the pump. Right, but what I want to do now though is I want to give you guys a real world example, something that we do with a lot of the guys that come through our station to help us better visualize or understand this whole process. So in this demonstration, our intake number 3 is going to be our tank to pump. So what we do is we pull the engine out on the approach, put it into pump gear, and go ahead and pull our tank to pump. Next thing we do is we have the rookie go ahead, unscrew discharge number 1 cap, and he pulls that lever. 2 things are gonna happen. A pressurized stream is gonna exit that discharge, and the rookie's gonna get wet, okay? You've got water entering the pump, being pressurized, and being discharged. So we shut that whole line down, we put the cap back on, and then I ask the question, what's gonna happen when we open up that 3-inch pony section? Most people's response is nothing will happen. No water will come out. That's an intake, not a discharge. But remember, we're utilizing a manifold here. Water that's coming in is hitting the pump. Any excess water that the pump is not utilizing is gonna flow back against those valves right there that are keeping the water from exiting those intakes. So if we open up intake 1, that pony suction, water's gonna come out, but it's gonna come out far less pressurized. Why? Because it's only being gravity fed. It has head pressure from the tank. So hopefully this helps you guys out. Water coming into our pumps can come in through multiple intakes that converge into that intake manifold before it hits the pump. Okay, this is gonna lay the foundation for things that we talk about down the road. So again, hopefully this helps you guys out. We'll see you guys next week.
Once a positive water source is established, the supply engine can refill its tank while still feeding the attack engine. The attack engine can then refill its tank while supplying the attack crew. When the fire is out, make sure to shut all lines and supplies down in the proper order. Nozzle then attack engine, from the supply engine to the attack engine, and finally the hydrant. Not this or this. Cavitation can usually be determined by the sound emanating from a pump while operating. If the pump sounds as if many small stones were passing through with increased vibration, cavitation usually exists. Apparatus with fire command systems may detect cavitation, or what it thinks is cavitation, and automatically reduce throttle and remove itself from pressure mode. Know your apparatus. The following video will describe cavitation in more detail.
If a propeller spins quickly, it leaves a trail of bubbles behind it. As the bubbles pop, they make a lot of noise. These bubbles are not filled with air, but with steam. The steam is produced by the seawater boiling.
It is a well-known fact that water boils at 100 degrees centigrade. However, few people will know that at different pressures, the water will boil at different temperatures. If you increase the pressure, as in a pressure cooker for instance, then the boiling point of the water increases. Hence, the cooking is more efficient. Few people will know, however, that at reduced pressures, water will boil at lower temperatures. I have here a vacuum pump, and I'm going to turn on the vacuum. This flask here contains water, and we have it connected to a pressure gauge, and we're reading at the moment approximately 15 pounds per square inch, which is 1 atmosphere. I turn on the pump, you notice the pressure dropping immediately, and as the pressure drops, as we approach zero, bubbles start to form, and the water starts to boil. So here we are at room temperature, but at a significantly reduced pressure, almost a complete vacuum, the water is now boiling. Water boiling at 20 degrees centigrade at almost 0 pounds per square inch, a remarkable phenomenon, sir.
When a submarine's propeller turns quickly, an area of low pressure is created on the blades. This lowering of pressure causes the water to boil without heating up and produces bubbles of steam. This is called cavitation.
The formation of those bubbles is dependent on how fast we rotate our propeller. So the faster we go, the more risk we are for cavitation.
The Pennsylvania's propeller design is a closely guarded secret, but the basic principles of a quiet running propeller are known. Cavitation only occurs when a propeller spins quickly. Slowing the propeller down reduces cavitation and therefore noise. But slowing the propeller also reduces a submarine's thrust. To overcome this problem, the Pennsylvania's engineers developed a unique propeller with 4 additional specially shaped blades. These generate large amounts of thrust, but at much lower speeds. This way, the Pennsylvania produces almost no cavitation or propeller noise. She is a silent predator of the deep.
As you heard from the video, the result of cavitation is progressive damage to the impeller, breaking away small particles with each implosion. So why does this happen? Cavitation is produced under several conditions. The suction hose may be too small for the discharge volume, restriction in suction line at strainer, partial collapse of lining in suction hose, or the temperature of water being pumped is too high. So what are some of our remedies? Reduce the volume or pressure of discharge. Use a larger suction hose, 2.5 versus 5 inch. Shorten supply line if possible. Increase discharge pressure of supply line. Remove debris from strainer. Replace a faulty supply hose. And make sure you keep water circulating from pump to tank to keep it cool. Keep in mind that excessive temperature in the pump from not flowing water will also destroy the pump packing without cavitation being present. Since centrifugal pumps cannot pump air, positive displacement primers are required for drafting. The most common is the rotary vane primer, which is driven by an electrical 12-volt motor. The primer should not be operated for more than 45 seconds at a time. While operating, most primers use an oil supply to fill gaps between vanes and the pump casing. The oil is expelled with the air and water under the apparatus. We also have air primers. Newer pumpers are equipped with environmentally safe primers which do not use oil. These primers are impregnated with silicone-type material and will not have a reservoir. Maintenance of these primers are more cost-effective because they do not include a motor or reservoir for oil. This is just a simple example of how a draft works and will not take the place of a drafting class. Displacement pumps must overcome atmospheric pressure of 4.7 psi. As the piston is pulled, the atmospheric pressure moves water into the pump housing. The various gauges found on pumping apparatus are as follows. A compound gauge is capable of reading both positive and negative pressure readings, usually 0 to 600 psi for positive pressure and 0 to 30 inches of mercury for negative pressure. The master intake gauge is connected to the intake side of the pump when connected to a positive pressure source. Both static and residual pressures can be obtained. The master discharge gauge is connected to the discharge side of the pump. It measures the total discharge pressure of the water as it leaves the pump. Individual discharge gauges are one per outlet, measures pump discharge pressure for that specific outlet. Engine gauges include tachometer, oil pressure, and water temperature. Monitor these gauges closely. If a reading outside of normal operating range is obtained, correct the problem. If unable to correct the problem, shut the pump operation down as soon as possible. The main intake valve may be located on both sides of the pumper and/or front bumper. An auxiliary intake valve is a 2.5 and may be located on either side of the pump or the rear. The tank to pump valve is located on the pump panel and allows water from the booster tank to be discharged through the pump when in the open position. Once another water source is obtained, close the tank to pump valve. The tank fill valve, located on the pump panel, allows the booster tank to be filled from a supplied water source. It also can be cracked open to act as a recirculating valve in order to cool the pump. Individual discharge valves are used to control the flow of water from a specific discharge. These valves can be gated back to provide different pressures. Most can be locked in place by turning the handle a quarter turn. A fire pump drain valve is used to drain the pump and plumbing. An individual drain valve drains the individual discharges. The intake drain valve relieves pressure between the hydrant and the intake. If you have water leaking under the engine, you should be able to identify the probable cause quickly. Know where your leaks are coming from. The tank to pump valve should be in the open position. When using the booster tank, only one hand line should be used. The tank to pump valve should be closed to prevent tank being accidentally emptied if supply pressure drops too low. The booster tank should be refilled as soon as possible. So how large is your engine, ladder, or tanker's booster tank? How long will it last flowing an 1 3/4 or 2.5 line nonstop? How can you as a nozzle operator make this last longer? This basic concept about pressure applied to a confined fluid from without is transmitted equally in all directions explains why pressures are equalized in both lines of a Y hose. We figure pressure from one side, but we add the flow for the supply line. When using a wide hand line, you must have equal lengths and nozzles to perform correctly. We're going to talk about types of pressure. We'll be able to use these to improve pump operations. Static pressure, residual pressure, hydrant pressure. Net pump pressure. This is a measure of pressure actually produced by the pump. The difference in the pump discharge pressure and the incoming residual pressure. If the discharge pressure is 180 and the intake pressure is 90 psi, then the net pump pressure is 90 psi. Pump capacity is determined by the ability for the apparatus to deliver an amount of GPM at a set PSI for a draft of 10 feet elevation and 20 feet from the water source. An easy way to tell the capacity of a pump is that each 2.5-inch outlet is equal to approximately 250 gallons per minute. The amount of GPM will be reduced when RPMs increase and the pump begins to exceed 150 psi. This is one of the 4 limiting factors that reduce the capability of the pump. We'll talk more on that later. So I'll ask you, what's the capacity of your engine, ladder, tanker, or brush truck? The rated capacity can be exceeded with supply pressure. If the pump is receiving a positive water supply, not drafting, then a 1,500 gallon a minute pump can flow in excess of 2,000 GPM. It is being assisted in pushing an even higher volume of water through the pump. Calculating pump pressures. This is part of the formula that we will discuss later, and it includes the nozzle pressure plus the friction loss plus an appliance constant plus or minus elevation to equal your pump discharge pressure. Pressures are calculated based on residual pressure. Therefore, pressures must be set with the calculated volumes flowing. This is important for operators to know so that they aren't trying to chase the pressure settings as the nozzle is being opened and closed, especially in larger lines when they think they've reached the right pressure and the line hasn't been opened yet. Future trainings will be designed to reinforce this concept. This automatic nozzle is designed to provide 150 GPM at 100 PSI on a 1.75 inch line. This nozzle can switch between a 15/16 smooth bore and adjustable fog and is designed to provide 185 GPM at 50 PSI on an 1 3/4 line. This is a 15/16 smooth bore nozzle that is designed to provide 185 GPM at 50 PSI on an 1 3/4 line. The Blitzfire will provide between 100 and 500 GPM at 100 PSI nozzle pressure. It will flow 250 GPM on average. If water is not flowing, then you are simply looking at a static pressure in the line. Charge lines initially with nozzle pressure plus 25. The charging of hose lines should not be delayed in order to figure hydraulic calculations. Reference a friction loss chart after the line is charged and flowing to adjust. Inch and 3/4 pre-connected hand lines are those that are 200 foot in length. 2.5 pre-connected hand lines are those that are 200 foot in length. Remember to make adjustments to friction loss if the length changes. These are your 4 limiting factors: reaching your calculated engine pressure, residual pressure drops below 20 psi, a maximum engine RPMs are reached, throttle is increased with no additional increase in pressure or drop in hydrant pressure. These need to be memorized. This is the 10-20-30 rule. Note static pressure of your hydrant, then note the residual intake pressure while flowing. Then subtract the residual from your static. If there's up to a 10% drop, 3 additional lines can be utilized. If it's between a 10 and 20% drop, 2 additional lines are available. If it's between 20 and 30% drop, only 1 line is available. If it's over 30, you've hit one of your limiting factors. This is how you estimate your static pressure. Note your first residual pressure. We'll call it R1. Place another line in service with the same flow. Note the second residual pressure. We'll call this R2. Divide the difference by 2, then add to R1. This is the estimated static pressure. Then you can go back to the 10-20-30 rule. Here's an example. R1 is 90 psi, R2 is 60 psi, then subtract the R2 from R1 will give you 30. 30 divided by 2 equals 15. 15 added to 90, which is your R1, equals 105. This is your estimated static pressure. Now you can apply it to this 10-20-30 rule. If we take the numbers that we had in our example, you'll divide the 90 residual value by the 105 static value, and you'll get a 15% drop in pressure available. This will allow 2 additional lines of the same size to be utilized. Fire department connections. Most fire department connections are 5-inch for new builds. Some older FDCs require the use of 2.5 inch. This is a reminder it's a boost to hook to the FDC for the already existing underground water lines. If the FDC is damaged, you can still supply it by attaching a Siamese valve to the first floor discharge using 2.5-inch double female adapter. For FDCs, you want to maintain 150 psi at discharge. Be aware of a drop in pressure. A slow and steady drop could mean more heads are opening, indicating a fire is advancing. A rapid drop could mean failure of the entire system or your supply to the FDC. Relief valves, governors, and diverter lines. These devices are designed to relieve the excess pressure that may damage the pump. Governors on electronic pumps will adjust throttle while in pressure mode. This is why you may hear the truck throttle up and down on its own. This is also known as a dump valve. It protects the pump from water hammer and excessive intake pressure. You can also use a diverter line, or some trucks are made with a Ross relief valve. When using an intake relief valve, you should adjust slightly to higher than normal hydrant pressure. A relief valve may come by many names, but their purpose is still the same: to relieve any sudden shock to the pump when lines are shut down too quickly. Some are preset while others are automatic and constant. Side intake relief valves can be adjusted with an Allen wrench. This is a picture of the intake on ladder 33 for reference, and the bottom left slide is an example of the Ross relief valve. These are items that we should memorize: volume capability, GPM of all hand lines and their nozzle pressures, the settings for your relief valves, and common friction loss values. A quick reminder of those is 42 psi for 100 foot for 1 3/4 inch, 15 psi for 100 foot for 2.5 inch. We don't pump fires often, yet our actions or inactions as pump operators has a very real effect on the lives and safety of our coworkers. Pump operators have a personal responsibility to stay competent. Know your apparatus. Go out and learn your truck. Teach others about it too. Take the time to use a creeper and look at it again from a different perspective. Thanks for your time. Welcome to Hydraulics Part 2. This is where it gets interesting. Today we're going to use hydraulics, geometry, and math to provide quick water on the fire ground. Today's objectives are to review hydraulic calculations for friction loss and GPM, understand nozzle reaction and how to overcome it, tips for the fire ground, including housekeeping, discuss the use of the NFA formula during size-ups to help determine the first firefighting line. This is a review of the simple math that we talked about in the first presentation. For 1 3/4 lines, we're going to determine a GPM, multiply that by 3, drop the last digit, subtract 10, that gives the friction loss for 100 feet of hose. Then add that number to the nozzle pressure for the nozzle attached. Follow the same formula for the other diameters given. To review a simple GPM estimate by diameter, 1 3/4 lines can supply, on average, 175 GPM. 2.5 inch lines, on average, 250 GPM. For 5 inch lines, there's a wide range, between 500 to 1000 GPM. This is a simple way to remember line size in relation to GPMs produced. It can be used as a median value. It can be adjusted to be over or under for the needs of the fire ground. For example, on car fires or working during overhaul, members are typically alone and on their feet, moving the line from side to side. In these situations, it would be prudent to underpump. We have many nozzles here at Turtle Creek, so it is imperative that nozzle operators and engineers know which nozzle is attached to which line that's pulled for a fire. The configuration does vary from truck to truck. We carry fixed gallonage, high and low pressure combination, smooth bores, and a hybrid that can be a smooth bore or a fog. Every nozzle has pros and cons, but knowing how to use the nozzle you have can allow the nozzle firefighter to accomplish both tasks of extinguishment and smoke and heat removal. Newton's third law says, For every action, there is an equal and opposite reaction. This law applies to fluid dynamics in the form of nozzle reaction. The left chart shows the nozzle reaction for a 15/16 nozzle. This chart shows the recommended flow for residential firefighting is 150 GPM. That is a minimum. If you compare the nozzle reaction of smooth bores to that of the high and low pressure nozzles on the right side chart, you will see an additional jump in nozzle pressure without any gain in GPMs. Using a hydraulic equation for nozzle reaction and the website for the Vindicator nozzle flowing 210 GPM at 40 psi, the nozzle has a reaction of 67 foot-pounds, which is comparable to other nozzle, but at the cost of the weight of the nozzle. So unless you're one of these types, sustained nozzle reaction pressures in the 80s range will take its toll in stamina and work cycles on the fire ground. These are some best practices for hose control. The hip clamp on the left and the leg clamp on the right. This will allow any firefighter to move a single line by his or herself down a hallway on the interior of a fire ground. Here are some tips to overcome nozzle reaction that anyone can use with the right equipment and a little bit of time to set it up. For example, in commercial buildings or parking lots. The use of webbing or Prusik cord around the elbow will take the weight of the hose line and put it on the spine instead of grip strength. Entry point housekeeping. Do not clutter the entry point. No more than 2 lines in the same egress. This allows for the safety of getting people out, the ability to move either line, stacked weight, and room for other items like vent fans. Now we're going to discuss how to use some geometry and math to better our fireground operations. Everyone should have heard about the NFA or National Fire Academy formula. If not, here it is. This formula is a quick way to determine the GPMs needed by using your best estimate of the building size upon your arrival. This chart shows the most recent average square footage of single-family homes that a Google search could produce. Since these are the structures that fire departments have most of their fires in, we will use it as an example of how the math works. This is the average square footage of a home, 2,400 square feet. If anything is showing on arrival, assume no less than 25% involvement. When estimating the percentage involved beyond 25%, use better markers, like fire or turbulent smoke showing through open or broken windows and doors. Roughly estimate the length and width of a building. For example, 40-foot length and 30-foot width. Input this data into the formula. 40 times 30 equals 1,200 square foot. 1,200 times 2 floors that are involved equals 2,400 square feet. 2,400 divided by 3 is 800 GPM. Multiply this by the percentage involved, which is an estimate. For example, fire in front 2 rooms and smoke extending upstairs to a back bedroom. We'll assume 50% of the whole house is involved. Take your 800 GPM, multiply it by 50%, and it will give you 400 GPMs needed to extinguish a fire. In this scenario, both floors must be calculated because of involvement on the first floor and extension to the floor above. If no involvement on that floor, then there is no need for the additional calculation. So using both formulas, we'll use the NFA formula to determine GPM needed and line selection. This is completed by both an officer and the nozzle firefighter. They should be close in agreement. Use the hydraulic formulas to provide the proper GPM flow for the line selected. This is completed by the FAO or ATO. Will the line selected provide enough GPMs for the size of fire? If not, then stage a second line for the next company. We're going to go over some examples using our calculations. This is a mobile home. The fire is in a laundry. We've got smoke showing from an open front door and fire showing from the Charlie window. We'll assume a length of 20 feet by 40 foot width divided by 3, 1 floor is involved, 50% involvement. The calculation reveals that it's approximately 133 GPM. Adding that to our next equation, using a low pressure nozzle at 75 psi, your friction loss for 1 3/4 is 58. Your pump discharge pressure is 133. Where does your next line go if needed? Here's our next example. This is a ranch with a basement, but the fire's in the garage. One of the garage doors is burned away. We'll assume a length of 30 and a width of 40 divided by 3. Only 1 floor is involved, 25% involvement. It's just the garage. Our calculation shows that it's 100 GPM needed to put the fire out. And our hydraulic calculation shows with a nozzle pressure of 50, so we've selected a smooth bore, a friction loss of 70, and our pump discharge pressure is 120. Where does the next line go if we need it? The next example is a 2-story with a basement. The fire's in the kitchen. We'll assume a length of 30, a width of 40, divided by 3, 1 floor is involved, and 50%, because we have fire showing out of the Bravo and Charlie windows on our arrival. We're going to calculate a GPM of 200, and we're going to calculate a pump discharge pressure of 150. We've selected a smooth bore nozzle pressure line and a friction loss of 100. Where does the next line go? When it comes to apartments, it may be easier to picture how large a unit is to simplify our math. This chart shows the average apartment square footage is 1,100. The equation is similar, but replaces the number of floors involved with the number of units. Let's practice with one of these. We have a 3-story apartment, fire on the 2nd floor. We've got smoke showing from the 2nd floor balcony and reports of smoke in the hallway. We'll assume a length of 30, a width of 20, divided by 3, 1 unit involved. Because it's showing from front and back, we'll assume 100% involvement. This gives us 200 GPMs needed to put the fire out. With our hydraulic calculation, if we chose a smooth bore at 50 psi nozzle pressure, plus a friction loss of 50 plus 20, because we're using a 2.5-inch line to extend our attack line, we'll have a pump discharge pressure of 120. Is the first line enough to start or extinguish? And where does our second line go? Thanks for listening to this. In the future, we'll be practicing some task level evolutions to reinforce. We'll keep practicing. These calculations can be done on any run. Talk about it before you leave and see if the crew gets the same math. Hope to include these fire ground equations in the future after action reviews to show their value.